We are going to go through a review session for your exam that you have coming up on Monday, April 27th. So as a reminder, the exam will be open for 24 hours, but you will need to take it in a 2-hour window. So you want to make sure before you start that you are at a spot where Wi-Fi is the strongest, your computer is working effectively, all of that good technology juju is with you. Then you will start your exam. You will have to access it from your home page. There's a module under the syllabus I showed you in the announcement called Midterm 3 that will unlock at 9 a.m. And then you will start with the multiple choice. And the multiple choice will be similar to last time in that it will be shown one question at a time and the question will lock after you complete it. So you can't go back. So you'll go through the multiple choice. There are, I believe I said 18 multiple choice questions, so not a lot of multiple choice questions. You will complete that, then you will go back to the homepage, open up the short answer document, and type up your responses for that. There are 9 short answer questions. And again, I'll be using Verify to make sure that you didn't copy and paste from the internet or you didn't copy from a classmate. Use your brain, put things in your own words. And again, you have 2 hours to do both of those sections. I recommend you choose your exam block during business hours, if at all possible. Remember, I only respond to emails really between 8 and 5. And so if you start your exam at 7 p.m. and you run into some sort of issue and you can't download a document or something, I am not going to see that email until it is too late. So I recommend, again, you do it during business hours, but if you have other commitments going on, you can do it during the evening just now. You might find yourself in a tough situation. So that is the format of the test. Again, I'm asking you not to use your notes, not to use your book, not to talk to peers, not to look things up on the internet. I'm not going to make you pay for proctoring software because I feel like that is not the right answer at this time, but I'm just going to trust that you're going to do the right thing. So I will take any questions that you guys have right now about the format of the exam, and then I'll start the midterm about the material. Any questions you put in the chat? Okay. When you think of that, I'm going to switch to PowerPoint. Okay. Second, check. Okay. So this is going to be our review session for midterm 3. This morning section, the 9 o'clock section, you guys provided almost all of the questions. 10 o'clock section did not do as many, so I combined them because I feel like they're all, for the ones that I put in here, were all good questions, so I made one PowerPoint for both sections. Okay. So majority of questions came about the action potential, confusion about the steps of an action potential, what is an action potential, all of that. So an action potential is how neurons communicate with each other, how they signal. And we say that neurons have an electrical potential because at rest, they are polarized, which means that there is a difference in charge across the membrane. Inside of a neuron is negatively charged and the outside of a neuron is positively charged at rest. And this is called its membrane potential. And it's what gives the neuron its electrical properties. And it's built by these ion gradients, namely sodium and potassium, and the distribution of sodium and potassium inside the cell. Okay, so I tried to number them a little bit to see if that helps. We'll see if that does. So an action potential is the electrical signaling that a neuron does to communicate. And this happens instantly. So if you think the thought, snap my fingers, and you are instantly snapping, that's because an action potential has gone from your brain down to a neuron in your spinal cord. That spinal cord neuron has gone all the way to your arm, to your fingers, and is contracting muscles in your fingers, causing you to snap. So this all has to happen really, really quickly, okay? And so a neuron it starts with a neuron receiving a stimulus. Now, we've now talked about ways you can get some of these stimuli. So again, the neurons in your retina, your photoreceptors, the stimulus for them is light. A wavelength of light will stimulate rods or cones. For the hair cells in your inner ear, it's a sound wave that bends them. That's the stimulus. For the receptors in your hands and on your skin, we didn't talk about those, but it's pressure. So the touching, the physical pressure is what sends the stimulus. But for most neurons, it's a chemical released from a nearby neuron that causes the neuron that we classify as the stimulus, right? So it's a signal from another neuron that is the stimulus here. And what that stimulus does generally is it causes a depolarization. So it causes a change in electrical potential. And that is what opens up these voltage gated channels. So in the neuron, you have sodium and potassium channels that are normally closed. They're normally closed. They normally act as gates, keeping the sodium outside the cell and the potassium inside the cell. So normally these channels are closed. They keep the sodium out and the potassium in. It's like if you ever looked at like a herd of cows in an enclosure, right? Or horses or something, they're in an enclosure. They want to get out, but they're trapped. They're trapped in a high concentration. And in the same way, if you open up the gate, the animals will rush out. Okay, the same happens to sodium and potassium. So normally at rest, these channels are closed. However, if a stimulus, so say for example, we'll talk about your eyes. So if we have the photoreceptors, the rods and the cones in your eyes, and light hits it. So say we're looking at a blue flower. The blue light will hit our blue cones, and that will cause the channel to open. And for photoreceptors, it's a sodium channel. You don't need to know this, but it's a sodium channel. And so it will cause a slight depolarization because sodium will start to come in. And that depolarization changes the voltage. It changes the electricity across the membrane. It changes the ratio of positive charges to negative charges. And it makes the inside of the neuron, right where that light hit those receptors, it makes it more positive. So this voltage change will open up all the channels. So now all of a sudden, we've got a permeable membrane. We've got channels open all over the place. And sodium and potassium are going to want to follow their concentration gradients down. They're going to want to move from where they've been kept and squished in that area of high concentration to the relaxing area of low concentration. So step one, the neuron receives a stimulus. Some kind of stimulus, it depends on where the neuron is that we're talking about. So two, that stimulus causes a change in voltage that opens up our voltage gated sodium channels. And sodium will start to rush into the cell, causing a depolarization, a positive charge. Then step three, the sodium channel inactivates. Sodium channels get tired, they inactivate. Now step four is the repolarization phase. And so if you've seen those graphs where you can plot it, I'm not making you learn those graphs for a lecture, where you can plot the signal and you see like, oh, there's a rush of positive charge in and then a rush of positive charge out. You can graph the charge. So the depolarization is that first part, the rush of positive in. And now we need to bring the charges back. So we need to get some of that positive charge out of here. And that happens in the form of potassium. So potassium will go out of its voltage gated potassium channels and it will bring the inside of the cell back to negative. Step four. So step one, stimulus. Step two, voltage gated sodium channels open, sodium comes in, depolarization. Step three, sodium is inactive. Four, voltage gated potassium channels open, sodium flows out in a repolarization phase. Okay, so this is zooming in on steps 2 and 3. So normally the channel is closed. The sodium is stuck, it's waiting, it's at a high concentration. Then we get some sort of change in voltage, some sort of depolarization, whether that's from light, sound, a nearby neuron, something happens, the voltage reaches a threshold, and this channel is gonna open. It opens up, sodium rushes. We now have all this positive charge inside, okay? But then pretty quickly that sodium channel, it's a sprinter. You can't do anything else. It inactivates. Step 3, it inactivates. So this is what it looks like in motion. We got sodium channels opening, and inactivating, and then potassium channels opening, leading to that repolarization phase. A depolarization followed by a repolarization. And you can think of this as like a wave of charge. So a wave of positive charge coming in, and positive charge going out. Positive charge coming in, and positive charge going out. In with the sodium, out with the potassium. You can make some hand gestures to yourself if it helps you. It sometimes helps me. Okay, so that is considered our action potential. It's the depolarization followed by the repolarization. And it moves down the neuron in one direction because of the inactivation of the sodium channels. It can't go backwards. It can't affect more sodium channels where it already came from because those sodium channels are burnt out. Okay, it's like if you imagine a relay race. If you watch track meets, I've been watching the replays of the Olympics on NBC Sports sometimes. And I love those relay races, right? We got the sprinter and he passes the baton thingy to the next guy, and he runs a lap, and then he passes the baton to the next guy, and he runs a little bit, and then so on and so forth, right? Well, the baton can only move in one direction because the sprinters that already ran the race, they're exhausted. They're like passed out on the track. They're squirting Gatorade in their face, okay? So the same is true for the sodium channels. You can only pass that action potential to like fresh, rejuvenated, ready to go sodium channels further down the axon because the ones behind you, they're exhausted. They're lying on the track. You just gotta let them rest. Okay. So again, depolarization, sodium. Repolarization, potassium. Potassium channels are a little slower to open. Potassium is going to leave the cell and it returns the membrane to that negative charge. However, we end up with a problem because now we have all of our ions are in the wrong spots. We got to get the sodium out and the potassium in. And so we use the sodium potassium pump or the sodium potassium ATPase, which uses ATP to bring sodium out and potassium in, and it restores our concentration gradients here in step 5. Now, step 6 is about what happens when the action potential reaches the nerve terminal, the axon terminal. At the terminal, the voltage-gated calcium channels will open. So remember, voltage-gated means they'll open with the depolarization. They'll open with all that sodium rushing in. So sodium rushes in, causes a change in voltage across the membrane. Now we got positive charge on the inside, and the calcium channels are like, I love that positive charge, and I'm going to open up only when there's this positive charge near me. So they do. Calcium comes in, and calcium is the signal for the nerve to release its neurotransmitter. This is where the signal is converted from an electrical signal, a wave of charge, ions flowing around, to a chemical signal, which is a neurotransmitter. Voltage-gated calcium channels will open, calcium will come into the neuron will release neurotransmitter in step 6. Okay. I hope that makes more sense to people. If you still have questions about that, put them in the chat. Otherwise, I'm going to assume that my vigorous explanation of action potentials was a little bit more clear, helpful. If it was, you could also write that so I know that someone is listening to me. Otherwise, I'm going to just keep on going through other questions that we got. So some people want to know about reflex arcs. So what I want you to know about reflexes is that these are rapid, predictable, involuntary responses, and they occur over reflex arcs. If they're somatic, they're going to stimulate a skeletal muscle. This is the one time we talk about our skeletal muscles having an involuntary response, because we normally think of skeletal muscles, right, as the voluntary, like I'm choosing to pick up heavy objects sort of muscle. But with a reflex, you can't control. Autonomic reflexes will stimulate smooth and cardiac muscles that make the heart beat faster, that make you all sweaty, okay? They're rapid. And they have 5 elements, which are very similar to like a homeostatic control. So if we're back to chapter 1 or 2 when we talked about homeostasis, it's the same sort of thing. And what's interesting about a reflex arc is where the integration center is. What's interesting about the reflex arc, what makes it fast, what makes it special, is that the integration center is not the brain, it's spinal cord. So you are cooking yourself an elaborate meal. You're trying to, do something you saw on Instagram, right? So you're cooking up all your rice and beans in a fancy way, and you accidentally touch a hot stove. There are temperature receptors on your hand, so your hand will be like, that's hot, and it will send the it's hot up a sensory neuron to your spinal cord. And your spinal cord will be like, oh my gosh, that is a hot stove. We got to move the hand away before she hurts herself. And so the spinal cord will act as the integration center and send the signal down the motor neuron to the effector, to the muscles in your hand, saying, move the hand away. So you move your hand away. At the same time as it's sending a signal down your motor neuron, it's sending a signal up to your brain that says, by the way, that girl's an idiot. She touched a hot stove. So you're going to move your hand and then think to yourself, oh my gosh, that's hot. But by the point you think, oh my gosh, that's hot, you've already moved your hand. You've already saved yourself. And the reason you do this is because reflexes occur when you're in imminent danger. Now, a reflex in the biological sense is not you seeing a child drowning in a river and jumping into the river and saving that child. No, that is a good deed. It gives you brownie points and all that good stuff. It is not a reflex. It is not a reflex because you're thinking to yourself, I should jump into the river. You're thinking to yourself, maybe I should take my shoes off first. And then I should jump into the river and make sure my cell phone's not in my pocket and jump into the river. That's not a reflex. That's just like a good deed, okay? A reflex is where the spinal cord is making the decision. A reflex is when the spinal cord is making the decision. It occurs without conscious thought, okay? In a basic reflex arc. Now you have some more complicated reflex arcs that we're not going to get into, but the ones I want you to know for this class are these, we call them a two-neuron arc. Two-neuron arc. So they're occurring in the spinal cord, acting very quickly. The simple reflex arc here. So one neuron to two, integration happens in the spinal cord. Okay. Again, if you have more questions about that, please put them in the chat, or if something didn't make sense, or if it did make perfect sense and I answered your question, you can also put that in the chat. I'm going to keep going. Static versus dynamic equilibrium. So static equilibrium is your head in relation to gravity, the up-down. Okay? It tells you what direction is up. Dynamic equilibrium is rotational and angle, so you're moving around. So for your static equilibrium, we're looking in the area called the vestibule. We're looking at these membranes in the vestibule. And the receptors are called the maculae. So we have these maculae, and they've got little hair cells. Maculae has little hair cells, and the hair cells are going to be bent when these little salt crystals called otoliths bend. So if you are bending your head down, little otolith crystals are going to move. They're going to bend the hair cells in your maculae, which are in your vestibule, and that's going to send the signal, she's bending down, through your vestibular nerve, which will join with your cochlear nerve, and it will become cranial nerve 8, telling your body, watch out, you're bending down. That looks like in action. Little salt crystals moving around, bending hair cells in the maculae, which is in the larger area called the vestibule. Okay. Dynamic equilibrium uses semicircular canals. So we've got 3 semicircular canals, one in the X plane, one in the Y plane, and one in the Z plane. And they're filled with endolith, which is a fluid. When you move in a direction, if it's in the same plane as a semicircular canal, the fluid will move through that semicircular canal, and it will end in the region called the ampulla. It will end in the region called the ampulla. And the ampulla has a structure there called the crista ampullaris that has these little cupulas which have the hair cells. So we have an ampulla as the general region. The structure within that region is the crista ampullaris. Inside the crista ampullaris, we got the cupula, which have the hair cells. And they're going to bend when the fluid moves. So this is looking at it zoomed in. Again, the endolith is this fluid, and we're in the ampulla. We've got the crista ampullaris structure, and the cupula is the thing that holds the hair. And so when you spin around in circles like a figure skater does, you're going to move your endolith, you're going to bend your cupula, which is going to send a signal to your body, I'm moving in this direction. Again, let me know if you have questions about that was helpful, anything at all. Okay. A few people wanted me to go over the cranial nerves, and I'm going to resist reading you a chart because I know it's a Friday and no one wants to hear me read a giant chart, and it's also like not useful because you all can read a giant chart. And so I didn't get any more, I didn't get a lot of specific questions with the cranial nerves. People were more like, can you go over the cranial nerves? Okay. You have to know them. There are 12 of them. You have to know that what they do, and you have to know what kind of fibers they hold. Is it sensory fibers? Is it motor fibers? Or is it both sensory and motor fibers? We have 12 pairs of them. Most of them, why they're important is they're the nerves that are responsible for doing all the face and neck stuff. Everything that happens in your face and your neck uses a cranial nerve, which when you go through all of them, you're like, oh yes, eyes, nose, mouth, all accounted for with cranial nerves. The only one that doesn't do that is your vagus nerve. Your vagus nerve is your parasympathetic nerve that serves your thoracic and your abdominal cavity. Overstimulation of that will cause you to pass out. It's like a parasympathetic response. Your body being like, calm down. Sometimes it happens too much. This is showing you where they come from in the brain, which I'm not asking you to know. This is kind of a visual of what they do. So olfactory to the nose, optic to the eye, etc. And then I gave you some mnemonics to help you remember them. So on Old Olympus's towering top, a Finn and German viewed some hops will help you remember the names of each of the cranial nerves. And then some say merry money, but my brother says big brains matter more. Will help you remember if it's sensory, S, motor, M, or B, both sensory and motor fibers. So beyond that, I'm not sure how to help you. You really just need to make a series of flashcards, 12 flashcards, in fact, and learn the cranial nerves. Okay. We also have questions about the spinal cord, about the different horns of the spinal cord. So I wanted to start with this picture, which will show you like them in action, right? So we've got sensory receptors in our body. They're going to send that information on a sensory nerve. The cell body from your sensory nerve is located in this bulge that right before you reach the spinal cord is called your root ganglion here, and then it will go to the spinal cord and it will send that information up your spinal cord. When it goes to the brain, it crosses over. So information about the left side of your body is in the right side of your brain and vice versa. And then it will be integrated here in the cortex, and that response will come down your spinal cord on the other side. And then in motor neurons, the cell body is located in the spinal cord, and it sends its processes out. So the dorsal horn, the backside here, has the processes for sensory neurons. So dorsal is going to be your sensory input, and then the ventral horn has the motor. And again, for sensory, the cell body is located in this bulging structure called the dorsal root ganglia, and then the axon goes up the dorsal horn. And then in the ventral horn, this is going to have the cell body as well as the start of those axons here for your motor input. And they come together into spinal nerves. So unlike cranial nerves, which can be sensory or motor or both, all of your spinal nerves, all 31 spinal nerves, are both sensory and motor. They come together. This is showing your spinal nerves again, coming together of the motor and the sensory fibers. Okay. Finally, someone wants to know about the somatic and autonomic divisions of the nervous system. And so I thought I would show this overview again. So central nervous system is our brain and our spinal cord. Keep in mind that there are two different cell types in our whole nervous system. We're really talking about neurons and glia cells, two cells, neurons and glia cells. Glias are the supporters. Neurons are the ones that do most of the work. They have that action potential ability. They have an electrical capacity here. So brain and spinal cord are central. Peripheral nervous system are our cranial and our spinal nerves. Cranial and our spinal nerves that branch off and innervate everything in our body. We got sense organs are going to send information along a sensory nerve, which is an afferent pathway. Motor is that efferent pathway, and we can branch off our motor into things we control, our voluntary, our somatic division, and things that are outside of our control, our involuntary or autonomic division, which are our cardiac and smooth muscles, and then our glands. From the autonomic, we have things that prepare us for a stressful situation, that gear us up for attack, our sympathetic, and then we have things that bring us back to baseline, that hold us at that homeostasis. There's a parasympathetic. Okay, so this is what it looks like As an overview, our somatic system, we've got one neuron. It's going to have myelin on it. It's going to release acetylcholine directly onto our skeletal muscle and cause that skeletal muscle to contract. Whereas our autonomic division, these are two neuron chains. They have different targets, so they don't target skeletal muscle. Instead, they target smooth muscle, glands, and cardiac muscle. And they use a wider variety of neurotransmitters. Rather than just using acetylcholine, they're going to use acetylcholine, norepinephrine, and epinephrine. And again, they're going to have some different effects, okay? Whether it's sympathetic, gearing you up into that stressful situation, or parasympathetic, calming you down. And the autonomic branch, this is what controls your body automatically and helps you maintain your set points. This is what I just said. Somatic, only acetylcholine. Autonomic, this is the two neuron chain. They use different neurotransmitters. Okay, so that brings us to the end of what I had planned for the review session. So I will take any questions. Otherwise, happy studying, and we will have the exam Monday, and then a review session for the final exam will be Wednesday. I will post an announcement about that Tuesday.